being recorded and live stream. You have the mics working, right? Right, so good afternoon. You can hear me? No. So Santosh just went from here to his office to do the live stream. So the time lag might be 2 seconds. He said that he's going to live it. People are still coming in. Okay, so it's a pleasure to have Helen here, Dr. Helen Mason from University of Cambridge. She has been at Cambridge for a very, very long time. How many years? 30, 40 years. So she did her PhD from University College London with Professor Mike Seaton, a great atomic physics theorist. And then after completing, she moved to Cambridge, and there she's been ever since then. She worked with, in the beginning, with Professor Helen, and then she rose through her career, became head of the group, atomic astrophysics group, and she retired from there in 2017. Her expertise are essentially in ultraviolet and X-ray spectroscopy and atomic physics to understand those lines which you see in solar atmosphere. So she has been working throughout the years on looking at these lines and trying to understand what the solar atmospheric conditions are using those lines. And she has been, because of these lines, interpretation requires a lot of atomic physics theoretical calculations. She, and along with her colleagues, Kendir and others, they founded this Gianti, not the wine, but the Gianti database, which is extensively used in solar atmospheric physics. She's also worked quite a lot on public outreach and engages with the schools and school teachers at large. In a big ways, has been to teaching at different places, including Tamil Nadu and South Africa. And for all her achievements, she was given OBE, which is Order of British Empire, which is similar to Padma Shri in India, in 2014. And also she was given Annie Maunder Medal of the Royal Astronomical Society in 2018. She, because of her long career and focusing on solar spectroscopy, she has been involved all the way from OSO 5, which was much before than we ever were in this world, and all the way through in the most, the newest spectrometer, which is XSM on Chandrayaan 2. So covering all through all the space missions which went on to the solar atmosphere. And today, she would be taking us through all those results and what new results are coming up from the XSM.
Thank you. Do we have a pointer?
Yeah, that's the pointer. So that one. Okay. And you can go back and forth with the announcements.
Well, it's a great honor to be here at IUCAA. I was last here in February 2020 at the big meeting that President Tripathi organized for East Asia, and haven't really traveled very far since then, just within the UK and Europe. So this is my big first adventure, and my big first adventure is to come back to India, because India is a country that I love and that I've visited many times. So I'm very happy to be here with you, and I want to share with you one aspect of the work that I've been involved with over the years. So I want to focus on the X-ray part of the spectrum. I've done a lot of work with SOHO, I've done a lot of work in the ultraviolet and other areas, but I thought I'd just focus on one aspect today to share that with you. And as Dergish said, taking it from very early observations right through to working on Chandrayaan-2 with the XSM team at the Physical Research Laboratories in Ahmedabad. So I was head of the Atomic Astrophysics Group, and no one is an island. We all work with colleagues, and I love to collaborate with my colleagues. Any spacecraft that you work on is not an individual effort, it's a team effort. And you'll find out that in science, although you can do individual work, majority of work nowadays was as a team. So these are members of my team, past and present. You might recognize this person standing here who worked with me in Cambridge for quite a while. And Sargam here originally came from IUCAA, and then she came and did a PhD with me and is now a postdoc in Glasgow. I think she came back to IUCAA for a while as well. Giulio Delzana here, I've worked with very closely. You'll hear me mention his name many times. He's now head of the group in Cambridge. And these other colleagues, Peter, Steve, Yarrow, Andrew, other colleagues there I've worked with and now spread around the world in different places. Now, you might think it's strange that I'm going to talk about X-rays and I'm starting off with a picture of a total eclipse of the sun. But I have to say, I'm really passionate about total eclipses of the sun, so I wanted to bring that in somewhere. But when you have a total eclipse of the sun, the moon exactly blocks out the disk of the sun, and what you see is this beautiful crown of light, the corona, the solar corona. And that's one of the things that we are working on, and I'll tell you why in a minute or two. But it's an awesome experience, so if you ever get the chance to experience a total eclipse of the sun, please do take that opportunity. I've experienced it 3 times, and each time has been very different. But you'll see here a lot of structures here, and those structures are in fact caused by the magnetic field on the sun. So the sun has a magnetic field, and because the gas is hot and ionized, it traces out the magnetic field. But if we use a spectrometer to look at that solar corona, what do we find? Well, they found something very surprising back in like late 1980s, and it took them a long time to understand what they were actually seeing. If you use a spectrometer and look at the corona, you see some spectral lines in the visible, the green spectral line at 5303 in angstroms, 530 nanometers, and a red spectral line here. And it took them a long time to understand what these spectral lines were. They tried to assign it to an element, and helium was found on the sun, and helium comes from the Greek name helios, so they thought, well, it had a lot of luck with that. So they invented a new name called coronium for a new element. But of course, you'll know that coronium can't be fit into the periodic table anywhere. It doesn't exist. That was a science theory that went down a cul-de-sac. It really didn't go anywhere. But after a lot of work, what they realized was that these lines were formed by just iron, which is very highly ionized. So it's very, very hot. And because it's hot, it would normally have 26 electrons, but a lot of the electrons have been stripped off it, and you end up with 13 electrons being stripped off. Confusingly, we sometimes call this iron 14 or Fe plus 13. But in order to strip that many, it needs to be very hot. So that corona they discovered was 1 million degrees. Now, that was a surprise. They didn't expect that. And yet the surface of the sun is around about 6,000. The core is 15 million. But the surface is around about 6,000. What they discovered is this corona was very hot. And that's one of the things we've been seeking to understand. And we have made a significant amount of progress. We haven't fully solved the problem yet, but it's something we're working on. It is something, again, which Aditya will be addressing as well. So if you look, the people who identified this, Helen and Prof, did some very careful laboratory measurements along isoelectric sequences, and these are the transitions between the ground levels of iron 14 and the red line iron 30. And they discovered that these lines were due to those transitions. Now, interestingly enough, Dergish mentioned that I worked at University College, and the first thing I was given when I went to University College was some eclipse data to analyze. And that eclipse data had some of these lines. It wasn't as long ago as 1900s, but it was quite a long time ago. And the eclipse data had some of these lines. And I had to do some atomic physics calculations, which enabled us to interpret the intensities of those lines. So this is my supervisor here, Professor Mike Seaton, who was a very eminent atomic physicist, and led a big atomic physics group. And I carried out calculations for quite a few of these coronal ions, which were the first accurate calculations that existed, and many people used them. And this is Dr. Alan Burgess, who worked with Professor Seaton, and Dr. Burgess was my supervisor when I moved to Cambridge. And Dr. Burgess was also a very eminent atomic physicist and responsible for some important processes with regard to ionization and recombination called dielectronic recombination. So if we superpose the green line and the red line, these are images taken by Shadia Habal, and this is taken in a green filter, and this is a red filter. You can see again how beautiful the solar corona is, and how these lines trace out the structures, the complex structures of the magnetic field. Now, because the corona is so hot, it emits very strongly in the ultraviolet and the X-rays. And this is a very old image. It's not a photo because it's taken with a special camera to see X-rays. It's a very old image from the 1970s of the corona seen in X-rays. And you can see these dark regions called coronal holes where the magnetic field is open and where the solar wind, the fast solar wind comes from. And you can see the bright regions here, which we call active regions, which are regions where the sunspots are. So the sun is very active. It's not always constant. Sometimes it's very quiet, and sometimes it's very active. It has an 11-year cycle. So these are some of the oldest, not the oldest, because there were rocket flights as well, images in the X-rays from the sun. Here's a spectacular image from a Japanese satellite. So along the way, I've worked with NASA, with ESA, which is the European Space Agency, with Japanese colleagues very much more recently, and also with Indian colleagues. So this is a very international program of observation. So this is from the IUCAA satellite, a Japanese satellite, and here again in X-rays you can see the bright active regions where the sunspots are underneath, and then the dark regions are coronal holes where the magnetic field is open. And if you compare the X-ray emission in a quiet time during solar minimum with an active time, solar maximum, you can see the change in the X-ray emission during those time periods from solar minimum to solar max. At the moment, we're just coming up to solar maximum. We have been in a very quiet time, and we're just coming up to a more active time. Now, I wanted to refer you to some texts which I think might be useful. And the first one I'm going to mention is this book by Phillips, Feldman, and Landy. It's about the ultraviolet and X-ray spectroscopy. It's very detailed and it covers lots of processes. So if you're studying and you're interested in learning more about this, then I do recommend this book with several different sections that it covers. That's 2008. I'm also going to recommend a review paper that I did with my colleague Giulio Delzana. We have a series in solar physics called Living Reviews, in which people review the state of the art in particular topics. So if we want to find out about a particular topic, that's where we start looking. And we did a review of UV and X-ray diagnostics back in 2018. And again, it covers lots of different topics here. So if we take the spectral lines, what can we determine about the plasma? We want to find out. The spectral lines give us a lot of information. We can determine the electron density. We can determine the electron temperature. We can determine something called the emission measure, EM, which means the amount of material at different temperatures. We can look at the line profiles and line shifts, which can tell us about the movement of the gas, or turbulence, which is causing broadening of the gas. Now, we can also develop diagnostics to look for non-equilibrium processes. So we can't necessarily assume everything's in equilibrium. We can look for diagnostics for time-dependent ionization, for example, if things are moving very quickly, or for non-Maxwellian. We normally assume that the particle distributions, like the electron distribution function, is Maxwellian, but we can look for non-Maxwellian. So we've done a lot of work with some of those colleagues I showed you. So let's just very quickly think about basics, and then I can run through some of the results. So the emission line is just an emission between two levels, so the upper level J and level I. It's the amount of energy that comes out, and if it's photon, Planck's constant times the frequency. So you just get an emission line transition probability between two levels. And this is the only kind of complicated slide I'm going to show. But the intensity of the line is proportional to the abundance of the element times this function called G of T, which is we can calculate from all the different atomic parameters. We call it the contribution function, the electron density squared, and then integrated along the line of sight. So we have to break this G of T down, the Planck's constant, speed of light, wavelengths of the transition. This is the atomic transition, spontaneous radiative transition probability, the electron number density, the amount of the atom in a particular upper level, J, compared to the total amount of that ion. And this is the ionization equilibrium, the amount of that ion compared to the element. So X is the element. And we can derive, as I said, parameters like the emission measure. So what we need to do is to carry out some atomic physics calculations. And I'm going to simplify this a little bit, but the levels are excited in different ways. And as Doug said, we've simplified it because we've made it all. We've created a package called Gianti, which does all these complicated atomic physics calculations in the background, so people can then use it to analyze the spectrum. But what I'm showing here from Phillips's book is just the amount of, this is iron. So this is the amount of iron, this is iron 10 plus 9 here, as a function of temperature. So the amount of each ion is a function of temperature. And this is temperature going up from 10 to the 6, which is the coronal temperature. So we've got iron 10, and then we've got iron 14 here. And as we increase in temperature, when we have explosions on the flare, the temperature can go up to 10 million. So we get different ion stages. We'll see different ion stages as the temperature increases. And if we increase it still more, we'll go up and we'll see lots of different stages of iron. As we increase the temperature, more and more electrons get stripped off, and we can find out what temperature we're looking at by finding out what ion stages are there. So I mentioned Gianti and Dogenstein. We actually wanted to call it something. It's a collaboration between colleagues in Italy, the USA, and ourselves in Cambridge. As you can see, this photo was taken quite a while ago when I had hair as well. We're in Architecture, so we spent a lot of time in Florence. We wanted to call it something which was pleasant and brought good memories, and that we felt people would use it. And we were very successful because now it's universally used by almost all solar scientists who want to analyze spectra, but also those that are looking at imaging data because they want to see what lines contribute to different wavelength bands. So it was first released in 1996, a long time ago, but we update it regularly, and we're up to version 10 at the moment. So every couple of years, we've got a new version. We assess all the data that goes into it, and all the users have to do is to run the programs to get out the line intensities for particular densities, particular element abundances, particular conditions. And we're now up to over 4,000 citations. It's written in a language called IDL that solar people use a lot, but we're also now producing a Gianti Python version. I don't know whether any of you use Python at all, but there's a solar Pi version as well, which enables you to analyze solar spectra in Python also. So the first thing I'm just going to mention is the fact that if we take the ratio of two lines, the intensity of two lines, this is the intensity of two lines from a helium-like ion called oxygen 7, and this ratio might change with electron number density because of the way in which the lines are excited differently. So we see a change in the ratio of two lines from the same ion. This is oxygen 7 in this case. So as the density here is 10 to the 10, 10 to the 11, 10 to the 12, on the log scale, as the density goes up, the ratio of these two lines, it's called the forbidden line to the intercombination, but you don't need to worry about the details, the ratio of these two lines changes. We call this a diagnostic for electron density because it gives us very directly a measure of the electron density. And electron density is a very important parameter. If you're doing thermal modeling, you want to know what the electron density is of the plasma that you're modeling. And this is quite an old observation, 1980, of these lines. And you can see this is the forbidden line and the intercombination line. And you can see that the ratio of these lines has changed. So this forbidden line increases relative to the intercombination with time. These are different time sequences through a solar flare. And from the change in the ratio of those two lines, they were able to deduce that the electron density went up to higher than 10 to the 11. Now that is very high. The average corona would be at around about 10 to the 8. So that density has increased by 2 orders of magnitude. And the question is, how has that happened? Where is the material coming from? And we want to understand better how those solar flares are forming and what's feeding those solar flares. Now, I want to mention a very good colleague of mine, Anand Bhatia, who I worked with at Goddard Space Flight Center for many, many years. Goddard Space Flight Center was also the operations center for many of the solar satellites that I worked on. It was the operation center for Solar Maximum mission, for SOHO that I worked on for many years. But I also worked closely with Anand doing atomic physics calculation. Some might think it a little boring and a little tedious, but we actually found it quite exciting. So it enabled other people to analyze the data they had. So we used the codes that I'd learned to use from University College London, and also was learned to use these codes. And we calculated many sets of atomic data for different ions. And from this, ourselves and other people were able to interpret the intensities of the spectral lines that we saw. So this is just one example of a paper that we wrote together with colleagues and working on, quite a long time ago, working on OZO5 orbiting solar observatory, which actually saw lines in the wavelength range 90 to 200, but also in the shorter wavelength range, around about 10 angstroms. So very short wavelength, 10 angstroms, and also between 90 and 200 angstroms. And from the data we analysed here, again, we were able to use these density-sensitive ratios and get an electron density from the spectra that we were looking at. We were able to determine the amount of emission at different temperatures that were peaked around about 10 to the 7, 10 million Kelvin, and the density we got was, again, above 10 to the 11 at those high temperatures. Now, since that time of OZO5, we haven't had so many observations in this short wavelength, 90 to 150 angstrom wavelength range. Not in solar spectra. There's a lot in astronomy, astrophysics, you'll find more, but not in solar spectra. A little bit neglected. However, and this is this wavelength range from 100 to 140, this is the OZO5 spectrum for a flare, and these are ion lines, but we did have on the Solar Dynamics Observatory more recently, we had an instrument, we still have an instrument called EVE, and this is showing you before a flare and then during a flare, and you can see that during the flare, how all these high temperature, and these are all lines formed at 10 million degrees, how all of these high temperature lines shoot up during the flare. Previously, there's hardly anything there, and during the peak of the flare, we get all of these spectral lines shooting up. Now, I can get very excited about spectral lines. I'm sure you don't all get very excited about it in the same way, but it does enable, it's what it enables us to understand about what we're observing, which excites me. I'm going to turn to some observations with the Solar Maximum mission. Now, the Solar Maximum mission, launched in 1980, a long time ago now, was dedicated to studying solar flares. So it was a mission that had several different instruments, hard X-ray, soft X-ray, ultraviolet, all dedicated to studying solar flares. But it was orbiting around the Earth. So inevitably, with an instrument that orbits around the Earth, the really exciting things happen when the satellite is around the back of the Earth and you can't actually see the sun. So we would come in the morning and say, what happened last night? And we'll say, oh, there was an amazing solar flare last night, but we missed it because Solar Maximum mission was on the wrong side of the Earth. Now, coming back to Aditya later on, people might ask, why is Aditya at L1? Well, at L1, which is between the Earth and the Sun, the branch point, you will see the sun 24 hours of the day. So you're not going to be in the same situation that we were here, where everything exciting happens when the sun thinks, oh, they've all gone to bed. Let's have a bit of fun now. So these were all the instruments, but I worked on two instruments specifically, the ultraviolet spectrometer, which I'm not going to tell you about today, because I want to focus on the X-rays. And this is the X-ray polarimeter, and it had two parts. It had a flat crystal spectrometer and a bent crystal spectrometer. It had a coronagraph on SMM also, and this is some observations from the coronagraph that was on SMM. It only took a quarter of the sun, it didn't see the full sun. The coronagraph was a simulated eclipse, and again on Aditya L1, there will be a very sophisticated coronagraph, which will allow you to look at those spectral lines that I mentioned earlier, around 10 and 14, and also do magnetic field measurements, and it will be able to go quite close in to the surface of the sun. And in order to do that, you need to go into space. So it was failed, and at that time, we were able to go up into space and fix it. So we were all disappointed. It blew a fuse, I think. The electricity went off, it had blown a fuse. So it had to replace the fuse box. So they were able to go up on the International Space Station, the module, bring it in on the arm, and then fix it. So just like Hubble Space Telescope was fixed by the International Space Station, so the Solar Maximum mission was fixed by the International Space Station and lasted much longer. So if we have a flare, what we think is that there's some sort of magnetic reconnection taking place, and there's an acceleration of electrons or waves down into the legs of the loops, and then material, and this region here between the lower atmosphere and the corona. The corona is, as I said, about 10 to the 8th per cubic centimeter cubed, but below the surface is much more dense. But what we believe happens is that these points are pushed down. So basically, you're pushing down lower, so you're heating up some of the atmosphere down a bit lower. So the density goes up because you're pushing down. You go down lower, and the atmospheric density will go up, and then material evaporates back up. And we see evaporated material as a line shift. We see it as a blue shift if material is coming towards us, and a red shift if material is going away from us. And with the X-ray instruments, both on P78, which was another satellite, and on Solar Maximum mission, this blue shifted emission was studied quite extensively. So enabled to see something that we call chromospheric evaporation during flares. So this was a big area of study. I also studied it using the ultraviolet instrument, using a very hot line, which fell into an 21 line, which fell into the ultraviolet wavelength range, and which is now used in other satellites called ARIS, more recent. I'm not going to, even though I'd love to discuss that for an hour, I'm not going to discuss that. Right. So this is the X-ray spectrum, around about 1.8 angstroms, very short wavelengths. And we see lots of spectral lines here. Now, we've got the main spectral lines from iron 25, which is very, very hot. But we've also got a whole sequence of other lines here. And these are what we call inner shell transitions. They've come from an electron deep inside the atom jumping to a higher level. So an electron deep inside has been ejected, not one of the electrons on the outside. And when the energy levels fall back again, when they make the transition again, that's a big jump, therefore a very short wavelength. This just illustrates, and you don't need to look at the details, but this is a helium-like ion with basic transition here. This is the basic transition for ion 25, which I just showed you. You can have lots of other transitions from the ion below it, ion 24. So some of these transitions are formed and populated in quite complicated ways. And we call these satellite lines because this transition goes from an electron 1s 2p down to 1s squared, that's a ground. But if we add an extra electron, so we add a 2p, we have 1s 2p squared down to 1s squared 2p. A similar transition, but slightly different in the lower ion. We call those satellite lines. And these satellite lines can be formed in many different ways, and we can be used for different diagnostics as to whether the plasma is in equilibrium. So here's just an example from the bent crystal spectrometer of the main line, ion 25 here, and then all of these little satellite lines with different notations from ion 24. And again, in Gianti, we're able to simulate these, we're able to say what the intensities of these are like for different conditions, but it's a little bit more complicated to do that, and we're still actually working on some of that formulation. So here, let's think about a solar flare. This is a hard X-ray instrument. I'm not going to talk in detail about hard X-ray, but hard X-rays enable us to see where electrons are accelerated from. So a hard X-ray instrument measures in shorter wavelengths than I've been talking about. And here, for example, we've got solar flare taking place, and I think the structure is like this, with hot energy released above, where we have reconnection here. This energy is released here, and electrons are accelerated down, or we might have the eruption of a huge loop of material off into space. This is what we call a standard model for flares, so kind of like a cartoon model or a standard model. We could build that in more detail with a numerical model, or we could see if the observations confirm this sort of standard model. And in general, they do. In general, they do. We can look at heating and cooling processes. And this is a solar flare PET spectrum from the flat crystal spectrometer, which I worked a lot on, which is from 10 angstroms up to 15 angstroms. And I worked with Ken Phillips on this, and we were able to identify these spectral lines. We had to get the temperature, mostly iron lines, with some neon, some other elements. So most of these are very hot flare lines in this wavelength range. And this is the same instrument, flat crystal spectrometer, but this is of an active region, so it's going to be a little bit cooler. And the main lines I want to point out here are these lines at 15 angstroms and the line at 17 angstroms from an ion we call iron 17. Now, iron 17 is very, very strong in active regions, and it's quite important. And as I say, it has very strong lines here, and it has very strong lines here. And we can look at the ratio of these two. The ratio should be a fixed amount according to the atomic physics, but we can study these lines in detail. So these lines have been studied long ago with SMM, but we are studying them again more recently with a recent spectrometer, which I'll talk to you about. Now, one other diagnostic, I talked about element abundances, and you might think that the element abundances in the solar atmosphere are all the same, or in the sun, mostly made up of hydrogen and helium, but there are trace elements of lots of other, parts of lots of other elements. But actually, the amount of elements in different parts of the solar atmosphere are not the same. So in the corona, the element abundance in the corona is not the same as in the photosphere. So here, the ratio to the photosphere is 1. So if it's 1, it's going to be the same as the photosphere, the surface of the sun. But if it's not 1, then actually the element abundance is somehow different. And when you plot this as a function of the ionization potential, that means how you ionize the particular element that you're looking at for the first ionization from neutral to single charge. When you plot these as a function of the first ionization potential, you find there's a pattern. This pattern is seen in the solar wind, and this pattern is seen in the corona. And what we want to do is to understand what's causing this. We call it a fractionation. What's causing this FIP effect, first ionization potential effect. Martin Lamy in the States, Naval Research Laboratory, has done a lot of work on this, and he has a theory called the ponderomotive force, which involves alpha in waves. And when the atmosphere is heated, then certain the layer which is heated, some of the ions are ionized, and some of the elements are ionized, some of the elements are not ionized. And those that are ionized get accelerated. So you can understand that those with the low FIP might have abundances which are higher than those that haven't yet been ionized. It's quite a complex theory. I'm not going to go into the details of it here, but we use this diagnostic called the first ionization potential to look at different parts of the solar atmosphere and determine where this process might be taking place. So in particular, we've done quite a lot of work looking at what we call these active regions. This is an X-ray image again from IUCAA, and you can see these very bright regions, X-ray cores, where the sunspots are. And we look at the very hottest part of these cores, and we try to understand these are loop structures because of the magnetic field structure. We try to understand the plasma conditions in these structures. Now, there's a theory of heating, which was developed by a very famous, eminent stellar or solar scientist called Eugene Parker, after whom Parker Solar Probe is named, who suggested that these loops, this is in the ultraviolet actually, but you can see all of these loops, these strands, get twisted up by the convection just beneath the surface of the sun. So the loop structure is made up of lots of strands. The strands get twisted up in the foot points, so if we straighten them out, that's one foot point, that's the other, start out straight, and then they all get twisted up. They don't actually like being tangled up, and when they reach a certain stage of being tangled, what we call magnetic reconnection happens, and they release magnetic energy, they kind of untwist, and then they end up in a lower potential state. We call this nanoflare heating because it's like lots of little explosions, lots of little flares going on around the place, and it can happen throughout these loops on different strands. Now, we've been studying and comparing models for this heating with what we see in the observations, the heating and cooling of the loops, to see if we can tie down the heating mechanisms. We've been doing this with a series of loops workshops. This is just one example. These people, Klimchuk, Surix, and Cargill, have been working on these models, famous theoreticians, to predict with their code EPTEL what we might see with this emission measure. That's the distribution of material. So the distribution of material here is a function of temperature, basically how much high temperature, how much low temperature there is, depending on the heating models. So this shows what happened with a weakly impulsive heating, weak nanoflares, and this shows what would happen with strong nanoflares. So Giulio Dazzana and I reanalyzed some of the data from the solar maximum mission, black crystal spectrometer, these ion lines, and in particular we looked at the shape of this emission measure, and we found that it went down very sharply. This is in the core of the active regions. We found the temperature is around about 3 million constantly in the core, and we found that this goes down. Now that's in line with what is predicted from some of those models. It's a very steep, but it's quite difficult to measure the steepness of this gradient. In the instruments that we had, we didn't really have good measurements to define this. But in the X-ray spectrometer, we did, because we could look at the ratio of iron 17 to iron 18. And if there's very little iron 18 in the ionization balance, then we can see that this is very steep. So we found a very steep line. We also were able to determine this FIP bias, the abundance bias, because we had other elements there, low FIP and high FIP, neon and oxygen. and we found it was 3.2. So, but those were quite old observations we had. It's a little bit more detail here. We're going to all the detail, but the fit bias, as I say, is around about 3.2. And we discovered that the iron was, we felt that the iron was enhanced relative to its photospheric abundances. So another paper that I wanted to draw your attention to is one that Julia was the first author, but it looks at what we really need to study this active region heating. What spectrometers, what wavelength needs do we focus on? And in order to resolve what the heating mechanisms actually are. And he felt that the 100 to 150 angstrom range was quite important to do that, although we currently don't really have a very good instrument to do that. So now I wanted to move on to more recent work. We've been very excited to be working with our colleagues at PRL, Ahmedabad. We've got a collaboration through the Royal Society going with them, and during lockdown, we've worked closely with them, Zooming every week, and produced quite a few papers. I'm not going to go through all of them. I'm just going to review some of the results that I particularly like. So this instrument is called the X-ray monitor, and it's being flown on board Chandrayaan-2, which, as you'll know, is a mission to the moon. And you might ask, well, why do we have a solar X-ray monitor on the mission to the moon? And the idea is actually, well, they're not that interested in the sun, but what they're interested in is the fluorescence back from the moon, so to determine the composition of the moon. But we're not interested in that. We're interested in the spectrum from the sun. And as I say, even before launch, we've been working with them a long time because we haven't had any X-ray instruments, soft X-ray instruments, in the wavelength range that they cover for a very long time, since solar maximum mission, basically, the FCS that I was talking about. So because this is orbiting the moon, obviously it's running into certain difficulties. It can't always see the sun. So there are certain times during the year when the observations are better. It's not at the Lagrange point, so it's not seeing it continuously. So we have to, if we're coordinating observations, we have to be aware that certain times are better. However, this instrument now, we're going in it's now going in kilo electron volts. There's two different languages. So the X-ray spectroscopist people were talking kilo electron volts, and I talk in angstroms. So I have to convert it. So 1 to 15 kilo electron volts is equivalent to 0.8 to 12 angstroms. So I have to do a little conversion in my head. And it has a very high cadence, so we get data back every second. It's very sensitive, so it can see sub-A class. Now, the way in which we categorize flares is we go A, B, C, moderate, and then X class, so that on their sizes, it can see flares, small flares, which are below the level of detection previously or classification as flares. It's far more sensitive than any other X-ray spectrometer. Any other X-ray instrument that we have at the moment. GOES is the one that is mainly used, but it's more sensitive than that, and it has this big dynamic range. So it has a lot of advantages. One of the disadvantages is that it looks at the full sun. Okay, so we see the full sun, whereas that wasn't true with some of the X-ray instruments. They had a smaller field of view. But in general, to get the amount of counts we need, we look at the full sun. Now, that means that you have to combine that information or that data with some way of seeing what we're actually seeing on the sun. And we do that by combining it with some imaging information from Solar Dynamics Observatory or other instruments. So here down the bottom, you'll see images from the Solar Dynamics Observatory as active regions rotate round. We see increases in the X-ray emission going up. So this is an active region period, active regions on the disk, here again, another active region period, and the active regions on the disk. And this is a quiet period. Now, this was launched a little while back in 2019 when the sun was relatively quiet, and maybe there was only one or two active regions going around at a time. But now, of course, the sun is very active. So we've got lots of things, lots of explosions happening. And it's somewhat more difficult to interpret what we're seeing because we have to trace it back. But in the early stages, with the quiet sun, in the active regions, but you can see, even during these quiet periods, this is the X-ray flux, you can see that it's not exactly quiet, it's not completely smooth, and this is not noise. These are actually small events happening. So there've been some studies of these, what we call quiet sun background, during this quiet phase of the sun. And then also during the active region phase, we can see again, this is not smooth. Sometimes we have small microflares happening within the active region. We have small flares, or we have larger flares happening within the active region. So lots of things we can study there. And they were kind of best studied early on in the mission when active regions were more or less isolated on the sun. But lots of papers and lots of information, as I say, which I'm not going to go through all of the details. But looking at the quiet sun, just looking at the heating could be these small-scale nanoflares even in the quiet sun, and they're able to determine the frequency of these small nanoflares and the frequency of the microflares and determine whether or not it fits into the pattern that's seen for larger flares. So one of the questions you might address is, large flares are seen in active regions, do the small-scale events occur everywhere, and if so, at what rate? So we were previously able to solve for some of this with other X-ray instruments, hard X-ray instruments, but this data is very, very good for doing that. So that's one of the first papers that was published in that regard. And here you can see different intensities of flares. So let's start off with the quiet sun, the pink one, and then an active region, then a B-class flare, the blue one there, and the C, it's like a bigger flare here, and then an M-class flare, a moderate flare here, and it goes right the way up to X-class flares now. And we're combining the observations of X-class flares with observations from, for example, Solar Orbiter. There's a hard X-ray instrument on Solar Orbiter called STIX, and you can combine the observations you get from XSM with STIX, which the team at XSM are doing, and use the software. The software they use is the Gianti software, so we've been working with them. So what you do is you fit the observations that you get here, you fit them such that you fit them with a temperature to get the right slope, you fit them with element abundances, and you can derive temperature, emission measure, element abundances from the observations that you have, because you can see here there are spectral features from different elements: nickel, iron, calcium, argon, sulfur, silicon, magnesium, and aluminium. So we have all these different elements giving rise to different spectral features, therefore we can get those element abundances. And there's a website if you're interested in the data. All of the data is available. It's all been made available. It's all documented. The team led by Santosh with Methan and Biswajit have worked really hard to make sure all of this data is available on the website, documented. If you want to look at it, if you want to use it for any of the studies or do anything with it, it's all freely available for you there to look at and use, up to the most recent data that they can put out there. So let's take, for an example, a flare spectrum. So the flare intensity here is increasing in XSM, goes down again. So we see when we have a flare and explosion, we get the X-ray emission increases, temperature maybe increases, and density increases, and then decreases again. We compare that with what we see from AIA as well to make sure we're looking at the right region. And this 94 angstrom has a high temperature line, so we're able to compare it with that. And it's also compared to this GOES other X-ray instrument, which is less sensitive. So we've studied lots of different flares. So we've taken several class B, that's quite small flares, in the range small to slightly bigger, we go B123 then. And these were the largest flares that we saw early on in the mission when the sun was relatively quiet, and their energies are small compared to X and M class flare. And what do we find? It's a little bit complicated, but this is the temperature rises. So we find the temperature rises. The background, the light grey, is just the X-ray flux. But here we can find the temperature rising from about 3 million, which is the core, active region core temperature, going up to about 7 million degrees. This is the emission measure, which also rises, going up. But here we have element abundances, relative element abundances, flip effect that I talked about for the different elements. Now, it's a little bit complicated here, but the top blue lines are the coronal measurements, and this green line here is the photospheric measurement. So what you will find in this plot is that during the flare, we start off at coronal values or thereabouts, but then what happens? Suddenly, this goes down to photospheric values. You'll see that with all of these elements, that's magnesium, aluminium, silicon, sulfur. Suddenly it goes down to photospheric values, and then it starts to increase back again to coronal values. Now, we believe this is direct evidence for chromospheric evaporation, for material coming up from the photosphere and filling those coronal loops. So what's happening is that initially we've got the coronal loops there, the flare goes off, we get those particles zooming down, and we then get chromospheric evaporation, and that material has still got photospheric abundances. It hasn't had time to get coronal abundances, and gradually it reduces back to the coronal abundances. They're very exciting. I found this very exciting observations, very exciting analysis, and the first time that I know that this has been directly measured in this way. We're still we're still struggling a little bit with why it goes back to coronal quite quickly, really quite work that one out. But as I say, the sort of model we're looking at, you get reconnection at the top of the loop, you get energy shooting down these loop legs, you get material evaporating back up again, as we saw way back with the XSM data. And the temperature rises, the emission measure rises, and the abundance goes down. We've looked at active regions, and this is the AIA data, the emission measure from the AIA data, and we can then predict what we should see with the XSM data from what we can derive from the AIA, and we get very good fits. This is just a double check using other instruments, Hinode ICE, which I haven't talked about, Hinode XRT, other instruments. So we do lots of cross checks to make sure we really understand and we're really accurate in what we do. Now, I've almost finished, but one other instrument I wanted to tell you about, which I'm also excited about, is an instrument called MAGICS. And this is a rocket flight, very different. It's not orbiting anything, so it's very short, just 5 minutes or so. And we had a flight in 2021. But this is covering the wavelength region that we're very excited about. In the 6 to 24 angstrom range, these dashed lines are another instrument on Hinode, but these lines here are from the MAGICS, in the MAGICS wavelength range, from 10 to 20 angstroms, and you can see they cover these flare temperatures, which we saw way back with solar maximum mission. If we look in detail at, say, just 3 lines, iron 17, 18, and 19, you can see this is the atomic functions for them, that is their G of T's, and they peak at different temperatures, so the lower temperature peaks here, and then it's iron 17, iron 18. But if we take the ratio of iron 17 to iron 18, we can work out exactly how hot the plasma is. It's a very sensitive ratio. And we can also work out what the different heating scenarios might be. So if we took that impulsive model and we had high frequency heating, we find that this ratio of iron 18 to iron 17 is quite small. If we took low frequency, that means not as fast between the heating events, then we get that ratio is quite large. So we can determine different parameters by looking at the iron 18 to the iron 18 to the iron 17 temperatures. I don't think that's quite right. Something's wrong there. Oh, that's with, yeah, sorry, that's predicted with the anything particularly low frequency, particularly high frequency. This is an instrument led by Marshall Space Flight Center, and we've just published a paper 2023, and Atheray is working on that also. You may know him. The rocket didn't work quite according to plan. We were hoping to get an active region, but we actually got a very small brightening, and it doesn't have a slit, so it doesn't have a spectral line well defined. It has kind of a squashed image line. So there's a lot of data analysis needs to go in to interpret the results, but this shows you the images and the lower temperature lines going up to design 17, other elements, abundances, but we're still able to get a lot of information out of it. And what do we find? We find that the high frequency impulsive heating supports the observations most. So we're looking to see what supports the observations. So in summary, we demonstrated the techniques. We demonstrated we could have an instrument in this wavelength range, and it will be flown again this year to look specifically in active region, and we're made more sensitive in certain ways. It also observed these lines I pointed out around 17 earlier on, the 15 to the 17 angstrom line. We found a little bit of problem with some of those iron 17 lines, and we think that some of the satellite lines might be contaminating it. But on the whole, we were quite pleased with the data analysis. So that's just a very initial results from MAGICS, but I think it's something that will give us, and Biswajit, who's at XSM, is going to be working with the MAGICS team as well. He's got a postdoc there. Aditya, I don't have time to go into detail because I've run out of time, I'm afraid, but it has a whole suite of different instruments to it. Dervish can tell you a lot about that's built and designed here. It's looking primarily at the chromosphere in the ultraviolet, but there are some hard X-ray instruments on it, SOLEX and aspects, and one of those will be similar to XSM but more sensitive, and produce some really interesting results. It has a Bell-C, which is like a coronagraph, and then it has instruments there sampling the solar wind, and it also has a magnetometer on it to sample the magnetic field. Very exciting to have your own dedicated Indian solar spacecraft, the first dedicated solar spacecraft from India to be launched and going to the L1 point. Now there's the suet. I think that, I don't know whether that was still here at that point, but it's obviously in a clean room, perhaps it's in Bangalore. But there's some details. And if you're around for the weekend, I think they'll have some models on display. Is that right, Dagesh? So some more information will be available. So that's it. So thank you all very much for listening.
Questions?
Yeah, I'm happy to take questions.
Nice overview.
Doesn't matter what they're about. Yes.
Thank you very much for a very interesting. So I have some more like a basic question. During the flare, I would imagine two effects which may require some correction what we have critical parameters. One, I would imagine that the sound, local sound film, very strong in the flare, and there will be some photoionization. I'm not sure.
Photoionization.
If there is the opposite concept back, that is one question. And related thing, because in the flare, things are changing very fast, and particularly with the magnetic connection, the particle distribution will not be much gradient.
That's a very good point. Yes. So there's two issues there. It says that we assume equilibrium. That's not always the case. Sometimes other processes beyond the ones we consider as traditional coronal equilibrium. He's mentioning one which is photoionization, which is a very strong radiation field, which could excite different levels in the atom, could be important. I think that's true, and I think that there's some instance in some transitions that could be the case. But a lot of the photoexcitation would come from the whole sun rather than from very small parts of the sun. But I think there are cases where it can affect individual transitions. The other very important aspect which you mentioned in solar flares you get acceleration of particle beams. So your general assumption about Maxwellian's distributions is no longer valid. And that's very true. And we've done a lot of work, obviously with the hard X-ray instruments. They can see the beams, they can fit a Maxwellian, and then they can also see a non-Maxwellian parallel tail for the electrons. So we've done a lot of work with our colleagues, Jaroslav Dudik and people in Ondřejov in the Czech Republic, looking at the possibilities of detecting non-Maxwellian distributions from using the spectral lines, because certain spectral lines are more sensitive. I didn't go into the details, but certain of those satellite bands are more sensitive. And we have had some success. So we have a paper where we do find that we think that you would expect when you get nanoflaring activities, you would expect non-Maxwellians, you would expect some feature like that due to reconnection. And we do have some evidence that in active regions, compared to the quiet sun, we do see some non-Maxwellians, although currently it's still quite tentative. But that is something that people are very interested in finding out more about. We've made some progress, but it's something that also with magics we've been addressing as well, possibility. But you're quite right, we're not in that equilibrium.
So if there is some kind of this non-physical so will that affect the physical parameters?
Yeah. So what we have, of course, yes, we can simulate a non-Maxwellian by something called kappa distribution, which is a mathematical notation for the distribution. And we have a whole version of Gianti, which is based around using a non-Maxwellian distribution. And that's published on a separate website, but it's developed by the Czech people in the Czech Republic, which is a kappa version of it. Yes, indeed, if you feed through non-Maxwellians into the models, they will give you different. In particular, they affect the ionization equilibrium quite dramatically. Yep.
In a slide, you mentioned about tangling and untangling of the players. Can you explain what are the factors that are responsible for the process?
Yes, I think that the idea is that the magnetic energy builds up because of the tangling, but I think it reaches a certain angle and then there's an instability, like am I right, Vegas? I'm looking at you for support here. An instability which doesn't allow it to go beyond a certain angle. That instability sets in. It's called magnetic reconnection, and then the magnetic energy that has been stored, as it were, is released in form of kinetic and thermal energy. So it's released in probably in a turbulent way, and that's what's causing that. But it's a process called magnetic displace, and you have to have certain conditions for that to take place. But that tangling is thought to be important throughout. It on a small scale, it could be causing the heating, which we think it could be causing. On a larger scale, the same sort of process, the tangling or the emergence of magnetic flux from beneath the surface, hitting flux that's already there and reconnecting with it. So that magnetic reconnection could be responsible for large explosions like huge solar flares or eruptions as well. So it can happen on different scales and different time intervals. So it's right from the little nanoflares, which we can't see, but we can infer from the distributions we're seeing, to the large flares that we can see and we can observe. Did you want to add anything on that?
No, I think so. Okay. Absolutely. First, red t-shirt. Are you there? Yeah.
So there is on Chandrayaan-2 there is something which measures the X-ray from sunlight. Wouldn't Chandrayaan-2 face the same problems which solar maximum the other satellite did because it is going behind Earth or something?
No.
Why would
Chandrayaan-2? No, because I think it goes around the sun, doesn't go behind the Earth, so it's between the Earth and the sun, if the sun's over there. So it goes around the sun with the Earth. So it's always between the the sun and the Earth. So it's not
does
going
have
to.
gaps, though, right?
Huh?
Sometimes during the year there are gaps where
Maybe if that, but is that a data transmission gap rather than a?
because it's not connected to the Earth, right, directly, so the data does not.
It's a data transmission gap rather than a positioning. So it's in the position
It's not
between.
going around the Earth. It's
going around. It's not orbiting the Earth at all. It's 100th of the way between the Earth and the Sun. So it's got a very small orbit to keep it stable, but it's actually in an orbit around the Sun, like the Earth is. So it is always facing the Sun. Unlike the Solar Orbiter and Solar Probe, which you might have heard of, which are going very close to the Sun, but sometimes they go around the back of the Sun, and the data transmission is very hard because it has to keep a lot of data on board. And when it's around the back of the Sun, you can't communicate with it because the radio noise and everything. And you have to wait, and it gives a little bleep to say it's still alive. So you have everybody staying up all night with coffee and waiting. And press that bleep, until it comes back and says, yeah, I'm still alive, I'm still here, when it comes round. Are there any problems with data transmission for Chandrayaan-2? Do you know? Because for SOHO, the data transmission was quite limited, so it did limit what we could do.
There is with Chandrayaan-2, you mean, or with Aditya?
With Aditya, sorry.
Yeah, I mean we have an antenna here.
Yeah.
So we will be in contact with the satellite only for 12 hours at
right.
first, and other 12 hours will be observing, but we'll be storing the data. So how much you can store the data that has to be transmitted in the next 12
so
hours.
You just have it in India, because I think with SOHO, maybe there were transmitters all around, because the Earth's rotating.
Right.
You need to have transmitters all around the Earth.
So with SOHO, you had one in the US and one in Australia. So
yeah.
Managed both. But here
and also one in Europe, I think. Yeah. I can't quite hear, I'm sorry.
Here's a very basic question on nanoflares.
What are the sources of formation of nanoflares in coronal?
Sorry, I can't quite hear
you. What is the source of formation of nanoflares in the coronal?
What is the source of formation of a nanoflare?
In the coronal region.
In the coronal?
In the corona.
Yeah, because of this twisting of the magnetic field, then the nanoflares are just a name for when you get a release of energy. So a nanoflare is a very small flare, so it's just a very small release of energy because of the twisting of the magnetic fields.
Nanoflares originate from the solar flare?
Say it again?
Do they originate from solar flares?
No, they're kind of. It depends if you wanted to say, it's a very small solar. If you, how do you want to categorize a solar flare? It's a very big event. So I would say it's on the same scale. It's just a very small event. So if you want to call it a flare, it's called just a nanoflare. It could be called a flare, but they're not in the same location as flares. A flare would be in an active region, but it's possible, and I think Dogish's instrument may be doing a bit of research on that. It's possible that these little nanoflares could occur in the quiet parts of the sun, not in the active regions. So the big flares will occur where the active regions are where the magnetic field is very strong. And that's why the release store a lot of energy, and that's why a lot of energy is released. But these could be happening in weaker, where the magnetic field is much weaker, and therefore there's not so much energy released at one time. It could be a whole sequence of them, but there could be a whole range of them, and that's something we're kind of trying to investigate at the moment.
You mentioned the coronium, which initially seemed like a new element, and then we determined it to be that of iron with 13 electrons stripped off. So how did we know that it was of iron and not maybe some other element like silicon with just 1 electron stripped off?
Good question. Each element has characteristic spectral lines. So each element has transitions from upper levels to low. The electrons can go into different orbits around the atom, so they'll move in particular ways. So it's not continuous. So the Bohr atom is in different layers, 1s, 2s, 2p, or whatever. They were only allowed to be in certain orbitals. And because the charge on the nucleus is different, those spectral lines that come out from the different elements will all be different. So you can identify the element by looking at the spectral lines, you know, where those lines lie. So I say it's a bit like a bar chart in a supermarket. You know, you can tell what you're buying because it's got all the information. And then as you ionize it, so you strip some electrons off, those change position, those transitions, the levels, energy levels change slightly. And the way in which they identified it was from iron is they did look at other elements. And they looked at a whole sequence of elements which had the same number of electrons, and they could see a variation. Some of them they could measure in the laboratory and see what the wavelengths were. But iron they couldn't actually measure in the laboratory, so they just had to extrapolate it. And that's how they found it was iron, because they extrapolated it from very careful laboratory measurements they made of the wavelengths of transitions of similar different elements with similar number of electrons in there going around them. But it was, as I say, it was a surprise, and it took 50 years, I think, for them to be able to do that. And very careful. Helen, who ran that laboratory, was a very, very careful scientist, very meticulous. So it came from laboratory work, a very careful laboratory work to do that.
One last question if somebody has, otherwise. Okay, all right. Let's thank Helen again for the fantastic review. So I'm not pressing it. I want to play.